There it is. Oh, I forgot to send out the link. I was gonna send out the link, so like, because like this is going on YouTube Live right now, but none of you know where my YouTube Live is. No, all of you don't care because you're all right here. But I'll send a link out at the end of this. Not that any of you care again, but that way when the recording goes up, you'll be able to get it. So Chem 129. What questions does everybody have?
I think on the homework, number 8 and 10, we're talking about.
So homework problem 8, problem 10. Is that visible on there? That corner is totally invisible, huh? Oh, the white balance went off again. Oh, that's not what it's supposed to do. The exposure is all off. There we go. Okay. For some reason, the camera's not working properly. I need like 4 programs to get it to work right now. Yeah.
Oh, the last two, 18 and 19.
18, oh, nice, yeah. 18 and 19, those are review problems, but they're a little tricky review problems. Sorry, that was 14B. 14B, that's another good one, and 17.
13 would be cool.
13 as well. Okay, we're just going to go through a bunch of them. Now, we should notice, does anyone have a copy of the homework just so I can see what we're looking at? Okay, if that's okay.
Yeah, sorry.
So let's see, if I remember correctly, a lot of these all have the same kind of flavor. 10, 14B, ooh, 14B might not be fair for the quiz, but 10, 14A, 13, 18 and 19 are a little bit different, but then 17, yeah, so a lot of these are going to be very similar. They're going to be like the calculations we've been doing in class already. And we'll just go ahead and take a look at these. Did you have another one you want to tell something?
No, so if 14B is kind of out of the quiz, so does that mean also 15B and C? That's the same.
Yeah, but let's look at them still, because we should be able to do these. These should be mostly review. Come and get comfortable, get your bags tucked underneath places. We can bring more chairs in from the hallway if need be, but everyone come in close. So let's go ahead and let's start with problem 8. What is problem 8?
Hydrogen sulfide decomposes according to the reaction 2H2S gas, and then a little sign, 2H2 gas plus S2 gas. At 700 degrees Celsius, the equilibrium constant is 9.3 times 10 to the negative 8. If 0.45 moles of H2S is placed in a 3-liter container, what is the concentration of H2 at equilibrium?
So there's a couple key phrases that we have to look at. So what I did was I wrote down kind of the technical information, right? I wrote down the chemical reaction. I wrote down the equilibrium constant. Go ahead and just call that the generic KEQ. And I wrote down the moles and the liters, and I wrote them down in a particular way because I know where the problem is going. What's the key word in this problem, though, that tells us what we're going to be doing? Equilibrium. Yeah, so we're going to be doing an equilibrium calculation, which instantly tells us to
Ice table.
Ice table. So we're going to set up an ice table, and all of a sudden it makes sense why I put it as 0.45 moles divided by 3 liters, because if we're doing an ice table, we need concentration. So 0.45 divided by 3 is going to be 0.15 molarity, assuming I can do math right. That's right, right?
Yeah.
Okay, great. So now we've got the molarity. We can go ahead and start thinking about this problem. Let's go ahead. Let's read that last sentence in the problem again.
If 0.45 moles of H2S is placed in a 3-liter container, what is the concentration of H2 at equilibrium?
So we are looking for the concentration of H2 at equilibrium. That's the thing we're looking for. Now notice, we're told what H2S is put into the container. Do we have any H2 in the container? No. Do we have any S2 in the container? No. So now we can go ahead and say, look, we should at this point do a Q versus KEQ calculation. Remember that? It's a 128 thing, where we compare products to reactants. We say, is our starting conditions already at equilibrium? Is it too many products or is it too many reactants? Compared to where KEQ, the equilibrium, is. Clearly, zeros in our products means we don't have enough products. And a lot of the time in this class, we're always going to have an obvious direction the reaction goes because we're going to have some zero that we need to correct. So in this case, our change is going to be minus 2x plus 2x and plus x. So I've done this all. My x's are set up in terms of 1 mole of S2. My answer is going to be a little bit off. I'm going to have 0.15 minus 2x. I'm going to have 2x, and I'm going to have x. So if I can find, that squeak is going to drive me crazy. So if I can find x, I can double that number, and that'll give me the concentration of H2 gas at equilibrium. So now all I have to do is I have to set up this equation. And we haven't done a problem like this, so hopefully you remember this. I'm starting to see, this is the problem with doing the quiz on Wednesday instead of Friday. I want just like one more class period before the quiz. So if we look at this, we're going to set up our equilibrium expression. Let's go ahead and set up our equilibrium expression. 9.3 times 10 to the minus, whoa, that's 8. Products over reactants, I'm going to have 2x squared times x divided by 0.15 minus 2x, also squared. Yeah.
Oh, no, I don't know if you're going to say it.
I might. What were you going to ask?
Since the K is so small, are we allowed to assume that the 2x at the bottom is 0?
Yes! Exactly. We are allowed to use the x as small approximation. Yeah.
So when we do that, do you want us to do like the calculation to make sure it's less than 5%?
We'll do that afterwards. So like essentially what we look at here is we've got this problem. We're going to set this up. This is going to be a cubic equation. Could we, if we had to, solve a cubic equation? I mean, if we absolutely had to, come on in. If we absolutely had to, everyone scoot a little bit more forward too. If we absolutely had to, I am certain that push comes to shove, we could figure out how to solve a cubic equation. I mean, we could hop onto Wolfram Mathematica, use their like equation solver and solve a cubic equation. But we don't really want to do that. This isn't a math class. You know, I'm sure you could solve quadratics and cubics if you wanted to, but we're going to go ahead and use the x as small approximation. So because KEQ is much less than 1, actually it's not because it's much less than 1, it's because it's much less than our starting concentration. Right? Because it's much less than our starting concentration. Essentially, because the KEQ is a really small number, we know that this amount that is going to change is only going to be a small amount. So that means that we can take this 2x and we can kind of ignore that 2x. Because 0.15 minus 2x is approximately equal to 0.15. Right? So if I have a billion and I subtract 1 from it, I still have about a billion. Right? And I could specifically say, no, you've actually got 999,999,999, but it's about a billion. So we're doing the same type of thing here. Because the KEQ is small, we know this is only going to shift a little bit. We can go ahead and set that up. That's going to simplify things because then I'm going to have 0.93 times 10 to the minus 8 times 0.15 squared. We still have to have that squared. Is equal to, if we do 2x squared times x, 4x cubed.
Wait, time out.
Go.
Is the 9, is it 9.3?
Oh, sorry. 9.3. Yeah, I just don't know why I did that. 9.3. You are correct. Can you solve that? Right, this isn't like a cubic or a quadratic. It's just do some algebra. quick check. How many of you were familiar with the X is small approximation? 5's being like totally got it, 1's being like.
first time I've ever
Yeah, I already done 4.
So, wow, someone missed doing that in 128. That's unfortunate. But I haven't made the quiz yet, so maybe that'll change what I put on the quiz. Because I thought all of homework 1 was going to be pretty much review. Yeah.
So once we find X, we multiply
So
by
let's
2.
go ahead. Let's get what the X value is. Everybody, calculators out. If you don't have your calculator out, you at home as well. No one's watching at home. I forgot to get the link out. Unless you're watching from last quarter because you still have this link. In which case, why are you watching this? You're not in this class anymore. I did this a little bit last quarter too.
Wait, do these videos like
Do
do they stay up there?
Yeah, I will be posting them afterwards, so you'll be able to go back and rewatch this.
Question?
Yeah.
I just want to clarify for myself, or like in my brain. So if for some, even though it's not H2S, if that was a solid, it would just be blanks rather than.
Correct.
Okay.
Right. So if we were dealing with the problems we did in class, we were dealing with a solid dissolving. We wouldn't include the concentration for a reactant.
Would it also be liquids?
Pure liquids.
Pure liquids.
Any
but
pure
aqueous
liquid.
ones would still be
Aqueous
nice.
solutions, anything that we can have a concentration of, right? So
Okay.
aqueous solutions, anytime we've got two components, we've got a solution.
Mhm.
In this class I mentioned last time, we're only going to be looking at aqueous solutions. So we're always going to use water as our solvent. So we'll have aqueous solutions. Gases, we can fake a concentration using PV equals nRT because you can have N over V
Oh.
is like moles per liter. So gases, even though they're not a solution technically, since they are particles in a certain volume, we can still fake a concentration for them. And so we do an ice table for gases and aqueous components. Did we get a value for X? What did you get?
0.0008.
Was that 3 zeros?
Yes.
Did you get any more digits after the 8?
0.57.
I'm going to go ahead and change that to 8.057 times 10 to the minus 4.
I have a question.
Yeah.
Do you care about sig figs in this course?
I do a little bit. So when I look at this, I probably should have been more careful. I should have said 0.45 moles and I should have said 3.0 liters. So we were looking at 2 sig figs. Then when we look at this would be 8.1 times 10 to the minus 4.
Okay.
Right? I should have been more careful. This is too many sig figs for the problem. I probably meant to have at least, I usually mean to have 2 to 4 sig figs. And if I have less than that, I've probably written a number down incorrectly. So we can go ahead and correct this to what I intended. Of course, if you did just put 8 times 10 to the minus 4, you're correct with sig figs. I probably meant to have 8.1 times 10 to the minus 4. What's the unit on this?
Molarity.
Molarity. Now this is our X value. So this is technically the molarity of S2 gas. You write that S2 gas. So this is our molarity of the S2 gas. That's the molarity of our S2 gas. I want to point out a couple things, right? First off, do we need to do the 5% calculation? If we look at this 8.1 times 10 to the minus 4 compared to 0.15, it's like a factor of 1,000 difference. So clearly you're going to have an error that's going to be on the order of like 0.1%. It's going to be a small mistake. We can just by inspection. Close enough, right? The only time we have to worry is when the X value we calculate is close to that initial concentration, then we have to worry and we have to double check. But as long as they're clearly very different and the X we calculate is much smaller than our concentration, good enough. So that's the first thing. Second thing I want to point out, this is not our final answer. Right? The problem clearly asks for the concentration of H2 gas. So we have to double that number. We're going to get 16.2 times 10 to the minus 4. And that will be our answer. You will notice almost all of the problems that you are asking about, besides 18, 19, those are a little bit strange, but pretty much all of the problems we're asking about are going to be calculations like this. We really do this calculation for like 4 weeks. So let's go ahead. Any questions about this one, or are we ready to move on? Let's go ahead, let's move on. Somebody else, even if you have to borrow a piece of paper, what does problem 10 say?
The molar solubility of a generic compound N2X is 5.00 times 10 to the negative fifth molarity. What is the concentration of each ion at the saturation point, parentheses, maximum ions in solution? How would you set up and solve for KSP? What assumptions must you make in the dissociation of M2X? Why is the calculated value of KSP higher than the experimental value of KSP?
Cool. So there's a couple things there. Again, as you read the question, I wrote down the technical information. I wrote down that we have a generic solid, M2X. I wrote down this was the molar solubility. I think I forgot a letter there. There's a T missing, solubility. I don't feel like fixing it. So we've got our generic solid. We've got the formula for that. We've got our molar solubility. We've got our black hit. There we go. There's a T in there now. That's not a K. That's a T. And I tried to write down all of the different things that the problems were asking for, right? So this is actually, even though it's problem 10, it could have been split into 10A, 10B, 10C. So we'll call it 10 part 1 was what's the M plus concentration at equilibrium and what's the X2 minus concentration at equilibrium. Notice I already jumped ahead, and because of the mole ratio, I can figure out the charges on these things. Problem part 2 of the problem was calculate the KSP. And then I think part 3 and 4 were kind of more conceptual, so I didn't write those down. Am I right? Does that look good? Okay. So let's go ahead, let's do part 1. Again, what's the key phrase?
Equilibrium.
At equilibrium. So we're going to do? Ice table. So let's go ahead and set this up. This is M2X solid. It's going to disassociate, double arrows, because now we're always doing equilibrium. It's going to disassociate to 2M plus aqueous plus, not S2 minus, sorry, X2 minus. Thinking about the last problem still. X2 minus, also aqueous. Now, keep in mind, this is a little bit funny because we're doing this for a solid that we don't know. So we don't actually know, like, does it dissolve a lot or does it dissolve a little? Until we look at the molar solubility. Question?
Why is it okay for you to assume that it's a solid? Because this is a compound.
Ooh,
Oh.
does it just say?
It says compound. A generic compound.
Oh, this is a generic compound? Oh, then we can't assume that. Sorry. This is a generic compound. So, okay, let's read that first sentence again and make sure that I'm not doing something wrong.
The molar solubility of a generic compound M2X is 5.00 times 10 to the negative fifth.
Right, okay, so I jumped ahead when I heard that. So there's a couple things there that let me assume it's a solid or a pure liquid, right?
Mm-hmm.
It's a generic compound with a molar solubility.
Okay.
Right? So we know it's a generic compound, and we're looking at the compound in its pure state. Whether it's a pure solid or a pure liquid, it's not going to have a component over here. For the sake of arguments, I just am going to go with solid.
Okay. Yeah.
Right, but it's because we have a couple key terms in there again, right? We have a pure compound that's going to disassociate. It could be a liquid that, you know, interacts with the water and breaks apart through the intermolecular forces, or it could be a solid that breaks apart through the intermolecular forces. Either way, when we set up this ice table, we're going to have the pure compound not contributing to the equilibrium. So either way, but yeah, that was a good catch. We can't actually tell for sure whether this is a solid or a pure liquid. We know it's not a gas, and we know it's not a solution already. So it's going to be one of the things we exclude. It's asking for the saturation point at.
It's asking for the concentration of each ion at the saturation point.
Okay. Now, one of the things that's strange is it's not saying whether it's saturation in water or not. Technically, we should specify saturation point in water. But again, because we're in a Chem 129 class, we're always going to be doing this in water.
The saturation point, does that mean equilibrium with solid?
Yeah.
Okay.
Right, and that's where we've got that extra phrase there. I gave the hint. The saturation point is the point when you have the maximum number of ions in solution, which is going to be at equilibrium. Right? There's a couple different phrases we use to say that we're talking about equilibrium. Maximum saturation point is one of those, or saturation point, maximum ions in solution. Those are both different ways of saying at equilibrium. So we know that we're doing this in water, so we're going to start with zeros there. We know that the change is going to be a plus 2x and a plus x. Notice again I'm setting it up so that it's in a ratio relative to the pure compound. I'm not going to call it a solid, to the pure compound. At equilibrium, I'm going to have 2x. I'm going to have x. Wow, that's just like the problems we did before, right? We're going to get 4x cubed again. So I'm going to have my KEQ equals 4x cubed. Follow-up question about the question. What's the second thing it asks for?
How would you set up and solve for KSP?
It is a solid. KSP is only for solids. Now, I should have been more specific when I said a pure solid compound. The question could be more specific, but there are hints in the problem that let us know it actually is a solid. So I can actually change this KEQ to a KSP. I'm going to have 4x cubed. And I actually have done a whole lot of work that I don't need to do. So, if we are solving part 1, the ions in solution at the saturation point, can I solve this equation right now? I don't have KSP, I don't have x. There must be some way that I have one of these things in the problem in order to solve this.
Is 5.00 times 10 to the negative x.
Yeah. Turns out the molar solubility, the 5.00 times 10 to the minus 5, is x. This value we're given is x. So get this. I didn't have to set up an ice table to solve this. X, the concentration of M plus is 5.00 times 10 to the minus 5. We didn't have to do an ice table. We didn't have to set any of this up. The concentration, 10. I need 2x. The concentration of x of our x2 minus, our compound here, is 5.00 times 10 to the minus 5. Our concentration of M plus is going to be twice that number, 10.00 times 10 to the minus 5.
Okay.
Yeah.
Do we know that the given molarity is also molarity for x because of the ratios?
Yes, right? So this is the molar solubility for the compound. Because it has a 1-to-1 ratio, we know that it's going to be the same concentration for ions in solution as the concentration of ions falling apart. We also know that all of the x comes from the pure compound falling apart, right? Because of this reaction, because of that relationship, the 1-to-1 ratio. So we could have actually solved part 1 without doing anything but realizing that the molar solubility tells us the compound's concentrations at equilibrium. This one's going to be 5.00 times 10 to the minus 5 molarity. This one's going to be 10.00 times 10 to the minus 5 molarity. If you want to call it 1 times 10 to the minus 4, that's fine. I just wanted to multiply by 2 easily. Now, I accidentally, when I set all of this up, was jumping to solving for KSP. Right, so to solve for KSP, we go through the ice table, we get KSP equals 4x cubed. We don't know the equilibrium constant, but we do know x. So now we can just plug that number in here, 5.00 times 10 to the minus 5, cube it, multiply by 4, answer. I can't do that in my head though, so I need your help.
It's 5 times 10 to the negative 13.
Is it really? That looks like a B. What are the units on that? Let's all scoot in more. There's somebody stuck in the hallway.
There are none.
There are no units. This is a KSP. Let's scoot in. Someone can sit right up here if they're comfortable with that. There are no units on an equilibrium constant. That's because every equilibrium constant is technically like K versus Q at standard conditions, which eliminate the units. But the main thing we need to know is there are no units. There are no units on this. So that would be the answer for part 2. Now, part 3 and part 4 are conceptual. Somebody who's willing to, can you read the first conceptual question?
What assumptions must you make in the dissociation of M to X?
What assumptions do we have to make?
It completely dissociates.
We assume it disassociates, right? We assume that it is going to fall apart. It's going to fall apart to 2m plus, or it's going to fall apart to an x2 minus. We assume that those ions that it's creating are not going to react with water, right? If we made something that was super reactive and it started reacting with the water, we couldn't do the calculation we just did. We'd have to do a chemical reaction and then have a whole different equilibrium. So we have to assume that it's not reactive. We have to assume that it's going to disassociate. And we have to assume that when the ions disassociate, the ions don't interact with each other once they're in solution. Yeah.
But if the KSP is so small, how can you say that it disassociates completely?
So when we're talking about the disassociation, we mean the ions, when they break apart, don't actually come back together, right? So they disassociate. There's still solid chunks left at the bottom, but once they disassociate, they completely separate from each other.
How did you get that assumption?
These are assumptions we make when we're dealing with ideal solutions. We should have gone over these in 128. I went over these in 128. Whether you remember them all from 128, that's a different thing. But so those are the assumptions we make. And then part 4.
Why is the calculate value of KSP higher than the experimental value of KSP?
If you've got plus ions and minus ions in solution, are they going to interact? At least a little bit, right? They're going to interact at least a small amount. Do you remember, this is definitely a 128 thing, do you remember the Van Hoff factor? Right, the Van Hoff factor, we had the ideal Van Hoff factor, which was always complete disassociation. The Van Hoff factor for this would be 3, because we've got the 2m plus and the x. But whenever we found an experimental value, it was always a little bit smaller than that because the ions actually do interact a little bit. So we could use the Van Hoff factor to say, how ideal is this solution behaving? Right? So we end up with the same situation here. When we assume ideal behavior, we assume complete separation, then we end up getting a value that is going to be different than if the ions are interacting a little bit. So it's asking us to remember ideal behavior versus non-ideal behavior. Yes?
You mean interacting with water, not each other?
Interacting with each other as well, they're definitely interacting with water because water is going to have a ion-dipole interaction.
Right, but they're interacting with each other, isn't that part of the equilibrium?
Not if we're doing it ideally, right? So we are separating out the interactions of them with each other, right? So we know that these ions end up in solution. You're thinking of the next step, which kind of is the defining feature of this, which is that saturation point, right? Because if we added anything else, then it would definitely interact in a precipitated form, right?
I mean, the way you wrote the reaction is that it goes back and forth. Isn't
Right.
The re-interacting part of moving back towards the solid?
Yes, but if we're at the saturation point, we're perfectly balancing where the ions in solution aren't interacting with each other. If we added one more ion, then it would interact, right? So we're hitting this perfect, so what you're getting caught up with, and I know you're going to do this because you think about these things, I had them in another class. There is a lot of nuance in here in terms of what we mean when we say equilibrium, right? We're doing a static picture, right? This is static, like there's solid, there's ions in solution, it's static, right? Once you hit what we call the steady state, right? Technically, there's a constant interaction of some salt dissolving, some reforming, and we've hit the balance between the forward and the backward. But when we are at that steady state, we can kind of do this static picture, which is a simplification of what's actually going on. For most of us, we can just think of this as like steady state, it's static. The ions in solution aren't interacting in the static version of the steady state approximation. Should we do another? Any questions about this?
Can you re-say what exactly the KSP was higher? In the shorter way, sorry.
The short way is the solution is behaving in a non-ideal conditions, right? The fact of the matter is the ions are going to interact a little bit, and that's going to reduce the experimental KSP.
And the experimental one would be the ideal one, while the calculated one is not.
Well, no, the ideal is like the calculated, right? Behaving perfectly is what we do on paper. If we went to a laboratory and actually measured this, we might get a different value.
Okay.
Okay. Other questions about this? Let's look at 13. Someone else willing to read problem 13?
The solubility of calcium sulfate at 30 degrees C is 0.209 grams per 100 milliliters. Calculate its solubility constant at this temperature.
I have to figure it out. Haha. It was rubbing against the metal there. Wish I thought of that earlier. Okay, so we are given the solubility in grams per 100 milliliters. We need to find the KSP. Let's go ahead and do some road mapping. Lowercase s is the solubility. KSP is the equilibrium constant. How do we get between the two? Yeah. We're going to use the molecular weight to convert the solubility into the molar solubility.
It's 0.20 grams. Yeah.
0.209. That's what happens when I do too many things at once. 0.209 grams. There you go. Okay. So we're gonna have we're gonna convert from solubility to molar solubility using molecular weight. How do we get from molar solubility to KSP? You can actually do that in one step using the ice table, right? And can we actually skip the ice table? What's KSP equal to? Right, we don't actually need to set up an ice table because we're recognizing the patterns already, right? For those of you that aren't recognizing these patterns, you're still going to be setting up an ice table. You're still going to do like 0, 0 plus x, you know, you're like, oh, it's x squared again. But as we start to recognize the patterns, like we can actually skip the ice table and say KSP equals x squared, where x is going to be our molar solubility. Yeah?
So in most cases, we can assume that the molar solubility is our x?
Yes. The way that we've set up every problem is so that x has a 1-to-1 ratio with the solid, so it's always going to be our molar solubility. I don't think there, I think we will always want to set it up that way so we have that extra simplicity. So really, this problem is just asking us to recognize that KSP equals x squared and then solve for molar solubility. It's not as bad as it looks when we first read it. Where does the 30 degrees come in? It really doesn't, right? As long as we have the solubility at this temperature and we're finding the KSP at the same temperature, we're okay. The only place the temperature becomes important is from things we did in 128, where we change the temperature and then KSP changes with temperature. Our equilibrium constant is temperature dependent. So we can do this problem, we can say, okay, what's the solubility at 90 degrees Celsius? As long as we stayed at 90 degrees, we could just do the whole problem as long as the temperature doesn't change. But it would affect our solubility. That would be a different number at 90 degrees.
So if you were to give us a problem where the temperature does change, we would have to change something first with the 0.209.
I don't think I'm going to give you any of those because you did those last quarter, if that's okay.
Okay.
You'd
I'm
have
fine
to
with
use
you not doing
you'd have to use the Van Hoft equation, natural log of K2 over K1 equals negative delta H over T. Oh no, negative delta H over R times the quantity of 1 over T2 minus 1 over T1. You all remember that, right?
Yeah, we've got it. You don't need
Yeah.
that. You don't need
You good, right? You good? Do I need to test on that?
I think
No, okay, great. Okay, so then all we actually have to do is say, okay, as long as we're at the same temperature, we're not changing temperatures. As long as we're not changing temperatures, we're just doing an equilibrium problem. So I'm going to need someone with a periodic table or a phone or some way to tell me what the molecular weight of calcium sulfate is.
136.14.
What is it?
136.14.
Close enough. 136 is probably close enough, to be honest. But so we're going to go ahead. We're going to do 0.209 grams times 1 mole per 136. I'm just going to go with 136. 136 grams. And I'm going to leave this as 100 milliliters for a moment, just so I can show you an easy way to do this. 0.209 divided by 136. I don't have a calculator.
.0015.
Is there one digit after that? 154 moles per 100 milliliters. 0.00154 moles per 100 milliliters. Now I want this to be per 1,000 milliliters. So I'm going to need 10 times more. Right? The conversion I did in class was I said, let's go ahead, let's treat this like a unit, like 100 milliliters. And then we're going to multiply by 0.1 liter times 100 milliliters. Right? Notice dividing by 0.1 is the same as multiplying by 10. So, and it also just makes logical sense that if I want, instead of 100 milliliters, if I want 1,000 milliliters, I just need 10 times more. So I'm going to have 0.0154 moles per liter. 0.0154 molarity. The other way you can think about this, you could also think about it in terms of times 1,000 milliliters per 1 liter. The only reason I caution you against this is because when we are changing to solubility, we don't want to evaluate that 100, right? We want to leave that factor of 100 on the bottom. A very common mistake is people will take that 0.209 and turn it to 0.00209. And then they still write it as grams per 100 milliliters, but they're actually giving me grams per milliliter. We don't want to evaluate that 100. We want to leave it as over 100 milliliters. So we just have to be careful about that when we're going backwards. But when we're going forwards, notice 1,000 milliliters per liter, also multiplying by 10. So whether you do it this way or that way, you're still just multiplying by 10. So that's our molar solubility, square that number, KSP.
Wait, so molar solubility is always X, right?
Yes, because of the ways that we are setting up the problems, we are setting them up such that molar solubility is X. That was 13. I bet you can do 14B without me now. You're always shaking your head no. Let's take a look at 14B. What's 14B say? Oh, sorry, I should have asked if we were on the kid and move on from that, but I've already erased it, so. We can do it again later if we need to.
Oh, I have a general question.
Yeah,
Do you want us to be using scientific notation or?
I prefer scientific notation. We avoid the problem of ambiguous zeros, and I'm pretty terrible at counting all the zeros over. And if you don't know how to switch your calculator to scientific notation, I can show you, and then you won't have those little scratch marks across the screen. I can show you now. Go ahead and hit second,
Oh, I do that.
and the button right next to it, and then switch it from flow to psi, and then hit equals.
What is happening?
Now you're in scientific notation, you don't need to catch. It depends on the version. I saw 3 people with the same version of the
Yeah,
calculator.
Oh, that's beautiful.
Yeah, so that will make life quite a bit easier. If you got a different version, if you got a different calculator, come talk to me, we can switch it. And it's just now you won't have scratch marks across your calculator, and since we want everything in scientific notation, it'll make life a little bit easier.
Oh,
You got the little loops.
Part of it's
Okay, so what's up with problem 14? Someone brave, read out the problem.
Says find the molar solubility of strontium carbonate when it has a KSP of 5.4 times 10 to the minus 10.
What was the KSP again?
5.4 times 10 to the minus 10.
And this was strontium carbonate?
Yeah.
Okay.
In a solution of 0.13
That's for part B?
Yeah.
Okay. So for part A, let's do part A real quick. If we're just doing it in pure water.
Mm-hmm.
Do I need to do an ice table?
No.
I mean, technically we can always do an ice table. We're just going to get KSP equals x squared. Take the square root. There's your solubility, right? We should be that fast at these problems already. A lot of people are like, your tests are too long. And I'm like, you're doing the full ice table every time. It's slowing you down a lot. Let's go ahead and let's move on to part B now. Part B, we kind of still need to do an ice table because part B, we're in a solution of
Strontium nitrate.
strontium nitrate. Does the nitrate matter? No, all that matters is that we've got strontium present. So if we look at the strontium carbonate, and we're going to strontium 2 plus CO3 2 minus. We're going to ice table this, of course, because we're looking at equilibrium. The strontium nitrate solution is going to make it so we don't have any carbonate, but the fact that we've got strontium nitrate means that there's an ion that we have in common between the strontium carbonate and the strontium nitrate. This is what we call the common ion effect. And I haven't defined that in class yet, but it comes down to doing the same thing that we did with the exasmall approximation earlier. Instead of having a 0 for our strontium, we have a, I forgot the value again, 0.13? We've got a 0.13 molarity there.
Isn't that the molarity?
Yeah.
But that was given.
It was given. Yeah, that was given. So then we can do our change minus x, plus x plus x. The reason it's plus x is, again, remember, I have to correct the 0. Technically, we should do Q versus KSP, but since our products are going to have a 0 value, I'm going to 0.13 times 0. Q is going to be 0. So that means I have to make more products in order to get to equilibrium. I'm going to have 0.13 plus x. I'm going to have x. And again, is 5.4 times 10 to the minus 10 a small number?
Yes.
Is it small compared to 0.13? It can be a small number, but remember, we're always going to be saying small compared to something. Is it a small number compared to 0.13?
Yes.
Yes, definitely. So we can go ahead, we can use the x is small approximation, we can just kind of say that. And now we've got KSP equals 0.13x. It's actually easier than A. Take your KSP, divide by that starting concentration, you've got your molar solubility in that solution. The place where you have to be careful, I believe, is there's a later problem someplace where you don't have a 1-to-1 ratio. You have to pay attention to whether you're doing a square root or if you're doing a cube root. You have to pay attention to should that 0.13 be squared or not. Like, it depends on how many ions it falls apart to. Since we were just doing a 1-to-1 ratio, it's just a straight division.
What did you just say? Sorry.
Oh, I said this is like one of the simplest cases because everything's a 1-to-1 ratio. So even with this one, we kind of didn't need to do the ice table. We just had to replace one of the x's with 0.13.
Okay.
If we had something that was not a 1-to-1 ratio, we'd want to be a little more careful to make sure that we square the correct thing.
For like in 15, like kind of basically the SR is like 2SR. So
Yeah.
we just square the 0.13.
Yes.
Yeah. But and we can still
What-
assume that
what
it's
was-
small.
What was 15? Before I just say yes to that, let me check.
15.
Yes, because it switches to silver. Yes,
Okay.
exactly. Exactly. Yeah. Question.
So my first try doing this, I just wanted to try it, and so what I did is, since they gave us in the solution of 0.13 molarity, I just plugged that in for strontium, and I left it as x squared, and I solved for the concentration of carbonate. So
Ah, but where did you? Where did you plug that in though?
into like the KSP equals x squared. So I separated it like into x times x,
Uh-huh.
and I plugged in the 0.13 for strontium, so I was left with the concentration of carbonate, and I just solved for that concentration, and I got
Yeah.
the same thing.
Yeah, that's a fine way to do it. You did the right thing, actually.
Sorry. Are you
Cool.
gonna post this video before class?
Yeah, I'll post it pretty much right after this.
Okay.
That'll only give you like 30 minutes to watch. It's gonna have to upload, so that might be a little slow, but it'll go on.
If the KSP was like, let's say a bigger number, would I still be able to do it that way, or would I have to do it, in that case, I have to do the ice table, right?
Yeah, so as we get to the point, like the reason that worked is because you made the x's smaller. This is a does a reaction happen question. This is a 128 question. This is simply does a reaction happen? How do we tell if a reaction happens or not? I gotta remember my. Anyone know sign language?
I had a dream last night that I didn't sign language. I don't know.
So essentially what we have to do is we have to look at Q versus KSP. Do y'all remember how to do that? Do you remember what Q is? I've talked about Q a couple times.
And then if Q is bigger than
Right.
KSP, then the reaction will go forward. Is that?
Yeah,
So you find Q for that point in the reaction.
yeah.
Okay.
And I always set it up this way. This way is always best for me. I have to remember to do this trick in class today. If we set, I'm going to change it instead of KSP. I'm just going to do it for generic KEQ because it works for any equilibrium constant. If KEQ is equal to Q, you're at equilibrium already. If KEQ is greater than Q, or KEQ is less than Q, let's change the way I say that. Towards products is fine. Or product favored. If KEQ is less than Q, the trick I have is if you always set it up so your equilibrium constant's on the left, the greater than less than sign is the arrow that points which direction the reaction is going to be favored.
So in this case, if you want the reaction to happen, you want the Q to be smaller than the K.
Yes.
Okay.
Because if Q is smaller than K, and also remember that each of these is products on top and reactants on bottom. It's just the KEQ is at equilibrium and the Q is not at equilibrium. So if Q is smaller, I need more products. I need more products in order to get to equilibrium. Right? I need a bigger number over here.
Thank you.
Yeah, no worries.
I don't know if this might help anyone, but the way I think of it is I just draw like a little line, like a number line. I just put K in the middle. I do a line, I put K. And if Q is less than K, it's gonna move towards the product.
That's great.
Right? And then
Yeah, so that's another way to do it. Is if you got a number line and K is there, if Q is over here, it has to go that way to get to K. If Q is over here, then it has to go that way to get to K.
I have a question.
Yeah.
So for those
That's a great way to think about it.
Like for changing the influence of the equilibrium, what kind of answer do you want? Do you want moves forward or product favored or towards?
Which problem is that? That's like
It's number 9.
number 9. Yeah, just say more products
Okay.
or more reactants or towards products or towards reactants.
Okay.
Yeah, that's fine. Let's see, I just realized that since the computer crashed, maybe it didn't actually save the video, which would be tragic.